I want to start with a number that's, well, it's almost impossible to visualize. 1 trillion.
Wow.
That's roughly how many pages of information are on the public web. And almost all of it is. It's natural language. Messy human speech.
It's an absolutely staggering archive. I mean, the biggest repository of knowledge in human history right there.
But here's the problem. We built it for us, for humans, but we expect computers to manage it. And computers, well, they don't speak human.
No, they don't. They speak binary logic. It's just 0, 1, true or false.
Exactly. So there's this fundamental disconnect. A computer is all about rigid rules, and human language is, it's the opposite. It's all about fluid ambiguity.
That's the core question, isn't it? How do you bridge that gap?
Yeah. How does a machine that only gets on or off figure out the difference between, say, I'm feeling blue and the sky is blue?
And that is the central question of the text we're diving into today: statistical natural language processing and knowledge acquisition.
Which, I have to admit, it sounds like a pretty heavy textbook.
It does.
But it's really more like a mechanic's manual for the whole modern internet. It gets into the invisible math behind your spam filter, your Google results.
And all those AI assistants that are getting a little too good at talking to us.
Right. It's the story of how we went from computers that just, count letters to computers that can actually read.
And to some extent, understand. And it turns out the secret isn't teaching them grammar rules from a textbook.
No, it's teaching them how to gamble.
In a sense, yes. It's about treating language like a game of probability.
Okay, so let's get into the nuts and bolts. The source text draws this really hard line between formal languages and natural languages.
Right. And a formal language is something like Python. It's designed so there's no ambiguity. If you type print 2 + 2...
there's only one possible answer. 4.
Exactly. It doesn't wonder if you're being sarcastic. It just executes.
And if you make one tiny mistake in the syntax,
the whole thing crashes. It's binary. It works or it doesn't. But natural language English is totally different. It's not about a sentence being 100% valid or 100% invalid.
The text has a great example for this. Not to be invited is sad. We all get that. It's a normal sentence. But to be not invited is sad. It's clunky. My English teacher would have circled that in red.
But you still understand it perfectly. It's not invalid in the way a broken line of code is. And that's why you can't just give a computer a list of every valid sentence.
The list would be infinite.
Yeah.
And even if you had it, you hit the ambiguity problem. The classic example they use is, he saw her duck.
He saw her duck.
Yeah. And my brain immediately splits. Did he see, a waterfowl that she owns? Or did he see her physically dodge something?
And grammatically, both are perfect. For a computer that runs on pure logic, that's a paradox. It crashes the system.
So you can't use logic. You have to use statistics. You don't ask, what does this mean? You have to ask,
how likely is it that it means X versus Y? You assign a probability. And to do that, you have to break language down into these little chunks. And that's where we get n-grams.
N-grams, right. This is one of those terms that sounds super complex, but the idea is actually pretty simple. It's just looking at a sequence of things, right?
That's all it is. An n-gram is just a sequence of n items from a text. And the whole idea is that language is predictable. If I give you a sequence, you can probably guess what's next.
It's like Wheel of Fortune.
Kind of, yeah. If I give you the letter Q and I ask you to guess the next letter.
It's you. It's almost certainly you.
That's a bingram. A sequence of 2. The probability of Q is incredibly high. The probability of QZ
is basically 0, unless you're playing Scrabble with some very strange words.
Right. And the source mentions that in a huge web collection, the probability of the word the was about 3%. But the sequence ZGQ.
Got to be infinitesimal.
0.000000000.
Wow. Okay, so the computer builds its whole model of language just by counting what usually sits next to what.
Exactly. Unigrams are single words, bigrams are pairs, trigrams are triplets, and the more history you use, the larger your N, the better your guesses.
And they actually tested this. They trained a model on their own book and then asked it to write new sentences. The unigram model was just a disaster.
Oh, yeah. It came up with logical R as our confusion a may write.
Just complete word salad.
Yeah.
But then they used a trigram model, so it looked at the 2 previous words.
And it started to sound like a person. It wrote, planning and scheduling are integrated.
That's a coherent thought. It's a bit dry, but it's coherent.
And that's the power of local context. But this raises a huge question. How do we actually measure if a model is any good?
Right, and they use this term perplexity, which is a great name for a metric. It sounds like a state of mind.
And in a way, it is. Think of perplexity as a measure of surprise. If a model sees the word united and the next word is states, it's not surprised at all.
Low perplexity.
Very low. But if the next word is refrigerator, the model is extremely surprised.
High perplexity.
Exactly. That unigram model had a perplexity of 891. The trigram model got it all the way down to 91. The lower the number, the better the model.
But this is where the math gets really, really tricky. And I think this is one of the most important ideas in the whole book.
Yeah.
What happens when the model sees something it's never, ever seen before?
The zero probability problem.
Right. Let's say you trained your model on books from 1990. It's never seen the word iPhone.
So in a strict probability model, the probability of iPhone is 0. And remember, these models work by multiplying all the probabilities in a sentence together.
And anything multiplied by 0.
The whole thing becomes 0.
So one new word, even just a typo, doesn't just lower the score. It crashes the whole calculation. It tells the computer that this sentence is literally impossible.
It's a mathematical black hole. And to fix this, we use something called smoothing.
Which, it sounds fancy, but isn't it kind of just lying to the computer a little bit?
I'd call it mathematical humility. You basically add a count of 1 to every single possible word before you even start.
So you're telling the machine, look, even if you haven't seen this word before, just assume there's a tiny, tiny chance it might exist.
Exactly. You're baking in a baseline of uncertainty. You're stopping the model from being so arrogant that it says, this is impossible.
I love that. Humility for algorithms. Okay, so we have these models that can predict text. Let's apply this to something real, something we all deal with, spam.
The eternal battle, spam versus ham.
Ham being the technical term for email we actually want to read. So this is a classic classification problem. You've got 2 buckets, right? How do you teach a machine to sort them?
Well, you start with features. The computer looks for things that show up a lot in the spam bucket, but almost never in the ham bucket.
And the source lists a few that are painfully familiar. Wholesale fashion watches. Viagra for $1.85.
Or the really tricky ones like, yo, do you deserve, with punctuation jammed in the middle to fool the simple filters.
This gets us to the bag of words model, which, I mean, it feels like the blunt force trauma approach to linguistics.
It really is. You're literally taking an email, writing every single word on a slip of paper and throwing them all into a bag. You shake it up.
So you lose all the word order, all the grammar. All you have left is the counts of the words.
But for spam, that's actually a feature, not a bug, isn't it?
That's what I was thinking, because spammers don't really care about syntax. They just care about keywords. If I see congratulations, winner, click, and claim in a bag, I don't need the grammar to know it's junk.
That's a great point. The bag of words model assumes that the presence of the signal words is way more important than the structure of how they're put together.
But there was this other theory in the source about spam that I found completely fascinating. The data compression idea.
Oh, yes, that's such a clever way of looking at it. It's based on the idea that spam is, well, it's repetitive, it's low entropy.
Meaning all spam emails kind of look like other spam emails.
Exactly. So imagine you have this one giant file with every spam email ever known inside it. Now, you take a new email that just came in, you tack it onto the end of that huge file, and you try to compress it, like zipping a file.
If it compresses really, really well, it's probably spam.
Right, because compression finds patterns. If the new email is just more of the same, the algorithm goes, I've seen this pattern before, and it squashes it down to almost nothing.
But if you added like a personal email from my mom to that giant spam file,
it wouldn't compress well at all. The words are different, the structure is new, it adds new information, so the file size barely shrinks.
that is so cool. It's literally using the file size as the spam filter.
It just goes to show there's so many ways to find a signal. You can read the words, or you can just measure the mathematical redundancy.
Okay, so we filtered the noise. Now we have to find the signal. Let's move from sorting email to, well, searching the entire world.
Information retrieval, the tech that built Google.
But before Google, we have to talk about the Dark Ages, the Boolean era.
Ugh, the era of Andy or N not.
It wasn't just that it was annoying to type out farming in Kansas. The whole approach was just, it was flawed. It doesn't understand how people actually look for things.
It's true. Boolean logic is binary. A document is either a match or it isn't. But human curiosity is a spectrum.
Right. If I search Kansas farming, a huge book that mentions Kansas once in a footnote is technically a match. and it gets treated the same as a textbook on Kansas agriculture.
Which is why you'd get a million results totally unranked. It was useless. We needed a way to measure aboutness.
And that's where the scoring functions come in, specifically TF-IDF.
The workhorse of modern search.
I always think TF-IDF is just the most elegant little equation. It's this perfect balance of popularity and rarity.
It really is. So
Anyway,
TF-IDF is term frequency, basically. How often does your search word show up in the document?
more is better, usually.
But if that was all you used, any document that just said the 1,000 times would be the top result for everything.
Which is where IDF comes in. Inverse document frequency. It gives a penalty to words that are super common everywhere.
So a word like the gets a score of almost 0 because it's in every document. But a word like farming is rarer, so it gets a boost. And Kansas is even rare, so it gets a huge boost.
So it lets the computer figure out that in the search, the Kansas farming, the word the is just noise, and Kansas is the real signal.
But even that wasn't enough. We have to talk about the big breakthrough. The reason we say Google it and not, Alta Vista it.
PageRank.
PageRank changed everything because it stopped just looking at the words on the page and started looking at the web as a whole community.
It solved the web spam problem.
Yeah.
Because once people figured out TF-IDF, they just started cheating.
Oh, yeah. They'd make a hidden web page that was just IBM 1,000 times to try and trick the term frequency score.
And PageRank just ignores all that. It treats a link from one page to another as a vote. But, and this is the genius part, it's not a democracy.
No, not at all. It's a weighted system. A link from some random blog is a tiny little vote. A link from, say, the New York Times website is a massive vote of confidence.
And the way they calculated it, this random surfer model, it's just such a beautiful thought experiment.
It really is. You
Yeah.
just imagine a user who is completely bored and just clicks on links at random, never uses the back button, just keeps clicking forward.
Over time, just by pure chance, they're going to end up spending more time on the big, important central sites because everything links to them.
That's it. The PageRank of a website is literally the probability that our random surfer is on that page at any given moment. It turned the structure of the web into a map of authority.
It was basically crowdsourcing relevance.
Yeah.
It just assumed that if a page is good, other people will link to it. And for 20 years, that's mostly been true.
Mostly. Of course, the SEO experts are always trying to find a way to game that system, too.
It's a constant arms race.
Ah.
But let's take this to the final level. We went from predicting letters to filtering spam to finding documents. The source text talks about one final shift.
The shift from finding documents to finding answers.
Information extraction.
This is where the computer stops treating text as just a bag of words and actually tries to figure out relationships.
It's the difference between searching for Lincoln and getting a list of websites versus asking, who killed Abraham Lincoln? And just getting the answer, John Wilkes Booth.
And for a computer, that's a gigantic leap. The source talks about a system called A's KMSR that tried to do this.
And the way it worked is, well, it's not what you'd think. You'd assume it needs to understand complex grammar, metaphors.
Right. Take a sentence like, John Wilkes Booth altered history with a bullet.
To a person, that obviously means he killed someone. But a computer just sees words. It doesn't know altered history with a bullet is a metaphor for assassination.
A simple keyword search might miss that completely. So how did AskKMSR solve it? Did it learn poetry?
No. It just used brute force.
It made an assumption. It assumed the web is so huge, so redundant, that somewhere out there, someone wrote the answer in a really simple way.
It's the infinite monkeys theory of search. You don't have to understand the complicated sentence. You just have to find the one page where someone wrote, literally, John Wilkes Booth killed Lincoln.
And that's what it did. The system rewrites the question maybe 15 different ways. Who killed Lincoln? The killer of Lincoln was killed by.
And then it just scans the web for those exact phrases and tallies up the names it finds next to them.
That's it. John Wilkes Booth is going to show up again and again next to those phrases. It's not intelligence. It's the wisdom of the crowd harvested statistically.
This leads to the last thing they talk about, machine reading. Systems like TextRunner that just crawl the web and try to build their own encyclopedia.
Right. TextRunner just skims the web looking for simple patterns like X is a Y or X established Y. It learns on its own.
And it pulled out millions of facts this way. But, and this is where I want to land, it also made mistakes. And the kind of mistake it made tells us everything.
You're talking about the water mistake.
I am. The system, with total confidence, extracted the fact. Water kills bacteria.
That's a pretty dangerous piece of medical advice.
So why did it think that?
It found a sentence somewhere on the web that said, boiling water for at least 10 minutes will kill bacteria.
And it just missed the word boiling.
It missed the condition. It saw water will kill bacteria and connected them.
And that really highlights the flaw in all of this, doesn't it? These systems, they crave simplicity. They're looking for X causes Y, but the real world is almost always X causes Y, but only if Z happens first.
That is the big takeaway. We've built these incredible systems by layering one simple probability model on top of another. Ngrams predict words. PageRank counts links. TextRunner looks for the simplest sentence patterns.
It creates an illusion of intelligence.
A very, very convincing illusion. But like the source says, systems like TextRunner work best when they actually ignore complex sentences and just wait for a simple one to come along.
They skip altered history with a bullet, and they wait for Booth killed Lincoln.
So the question we have to leave with is this. If our AI learns by skimming for the simplest, most direct, most blunt assertions, are we accidentally building a global knowledge base that has no room for nuance?
That's a haunting thought.
What happens to human knowledge when it's all filtered through a machine that actually prefers X is Y over the complex, messy, conditional truth?
Are we going to start writing simpler sentences just so the machines can understand us better?
We might already be doing it. Think about how you phrase a Google search. You strip out all the nuance yourself to get the right answer.
We're training ourselves to be machine readable.
Exactly.
Well, on that slightly terrifying note, I think that's a good place to wrap up. We've gone from counting letters to questioning the future of knowledge itself.
Standard procedure for a deep dive. I wouldn't have it any other way.
Thanks for listening. We'll see you in the next one.